Alright, so we're still on parametric equations of the line. But now, like I said, what if we want to just like shift that line? So I'll draw it again. So here's V, and here are its scalar multiples. I'll draw a couple, okay? And here's its line, right? So here's our line that we want to look at, and here's our x, y, z, and here's some like random point, okay? Let's say we want to hit that random point. We'll call it P naught, okay? This is called a little knot at the bottom. And that just means it's an actual point, a constant point. So if we have, let's say we want this, if we want to hit that point first of all, let's just look at it individually. So we'd have to draw a vector from the origin to that point, and that forms our new vector called O P naught, or like O for origin and then P naught, okay? So this is our new vector, and let's say it has coordinates x naught, y naught, and z naught. Okay, so this is just an arbitrary point, something I randomly chose out there in space. I could have chosen one over here or over there or whatever, but this just for demonstrative purposes, I just chose it there. Okay, so what I want to do now is take this. Remember, this was let's see. So we had our r of t here. Okay, so this was this line, this original line that I showed you on the last slide. But now we want the same line, but now we want to move it just up. I don't want to move the screen. No, I didn't want to do that. But I just want to shift it up, okay? So now I want to hit this line that goes through P naught, okay? And what we're going to do, how we're going to do that, is use this vector, this new vector, O for origin, and P naught, this vector here. And what we're going to do is actually take this. See how its base is at the origin and it ended up at P naught? We're going to take that and add it to every single one of these points on R of t. Okay? So let's say we have a point here. We're going to add O P naught to it, and that'll take us to our new location. Okay? And we're going to do the same thing at each of these points. We're going to add O P naught, and that takes us to this new line. Okay? We're going to do the same thing over here. Same thing there, same thing there. So eventually we'll move all of these points. They kind of just migrate up and to the right a little bit, okay? Just following the directions of that, OP naught, okay? So now the new parametrization of our line. So our new one, I'll call this our new R of t up here. That's going to be equal to the same thing that we had before, our same line here. So that was given by t times v, our vector v. But now, what we did to each of those points was just add the O P naught vector. Okay? So this is kind of like, I guess you can think of it as like our y-intercept. You know, on like the normal like y equals mx plus b. That's where it crosses the y-axis when x is equal to 0. So I was just making the analogy. When t equals 0 now, so when t is equal to 0, we just get that R of t is at O P naught, okay? It's at O P naught, so that would be this point right there instead of the origin, okay? So now we're living on this bold line up there, okay? So just in more expanded form, this is what we have. So R of t is going to be t of a, b, c, because that's what we set the vector v equal to, plus this new x naught, y naught, and z naught, because that is our, that's the components for OP naught, right? Okay, so this could be the vector parametrization of our new line, our bold line up here. And this is a very general parametrization, okay? So general parametrization, I'll just abbreviate parametrization, of a line in 3D. What you could also do is you can always simplify a little bit more. You could say that distribute the t in, so tb and tc, plus x naught, y naught, and z naught. Here we just use scalar multiplication, right? And finally, we could also say that this is ta plus x naught, comma, tb plus y naught, and finally tc plus z naught. Again, I'm just using vector algebra here. Here we just did addition, right? So all of these are correct parametrizations of a line in 3D. And just to note, if you want to get back to the origin, all you would have to do is make all of these, this x naught, y naught, z naught, equal 0, right? And then you're basically just adding the 0 vector, which means keeping the line in the same place as it was before. Okay? All right, so on the last one, on the last slide, we just found the last parameterization I listed looked like something like this, plus TA. I'm just switching the order that we see the additions going on here. And then we had z naught plus tc, okay? So what we have is this new line. So this is our x component, this is our y component, and this is our z component. So another way to write this is just saying x equals x naught plus ta, y equals y naught plus tb, and z equals z naught plus tc. So these three altogether are called our parametric equations, okay? So parametric equations. All right. So these are parametric equations, these three here, the set that you see, and the one above, because it has the arrow here, this was called the vector parametrization, okay? It's just like a technical distinction. So yeah, and again, our parameter or our parameter variable, either one, is t, okay? All right, so now let's do an example of what you might see. Okay, so what we're asked to find is a vector parameterization and parametric equations for the line through p naught equals 4, 2, 1 with direction vector v equals 5, 3, 7. Okay, so let's go back to our parameterization of a line, and our general parameterization of a line, that is, and that's equal to t times v plus op naught, okay? All right, so basically what we're going to do is just plug in what we have, right, our givens. So that's going to be t times v, v arrow, so that's 5, 3, 7, plus op, which is just going to give us 4, 2, and 1. Okay, so at this point, this is a vector parameterization already, so we could just leave it at that. But I'm just going to keep solving through because we need the parametric equations as well. So if we keep simplifying, we're going to distribute the t inside to each of these, right, that it's multiplied to. So we get 5t, 3t, 7t, and then we have our 4, 2, 1. That's our point floating around there. Okay, and the last step is just to add these vectors. So we have 5t plus 4, and then a 3t plus 2, and a 7t plus 1. All right, so this is our x component, and this is our y component, and this is our z component. So all of these that we have here are vector parameterizations because you still see this r arrow t, right? R arrow of t, yeah. Vector parameterizations. So these are all valid answers for vector parameterizations. And then we have our parametric equations. So our parametric equations will be the following. So those will look like x equals 5t plus 4, and then we have y equals 3t plus 2, and z equals 7t plus 1. Okay? And just more insight on what our parametric equations is, each of these tells you, like, because we have this parameter t, often it's thought of as like t represents time, or like seconds or minutes that have passed or something like that. And what each of these tell you is like, what is your x coordinate at time, like t equals 1 or t equals 0 or something like that. What is your y component when t equals a certain value, and what is your z component when t equals a certain value as well. Okay, so it kind of just allows us to divvy up and like look at all of our components separately. Okay? Alright, so here's an example of another type of problem that could show up. So the question's asking, do these lines intersect? So we're given two different parameterizations of two different lines, presumably, and we have an r sub 1 of t and an r sub 2 of t. So these are like two different lines in space, and let's say this is r1, and r2 is over here, and we're just asked, is there some kind of intersection point, okay, in space? All right, so what we're looking for is there an r1 of some t, let's say it's t1, such that this is equal to r2 of some t2. And what's important to note here is that t1 and t2 do not necessarily have to be equal. What does have to be equal are the x, y, and z values, because that would mean that at some t1 and at some t2, they meet at the same point in space. What we want to look for is the same, that x, y, and z components match up. That's the right phrasing. Match up at one time. Okay, at one time on each of the parametrizations. Okay, so like I said, in space we want them all to meet up at this one x, y, z point, some point here. Okay, so let's look for that. So the way we do this algebraically is that we're going to take r1 of t. We want to basically get it into parametric equation form. Okay, so that just means working everything out, and the first thing we're going to do is distribute that t in. So we have a negative 2t, a 3t, and a 5t, okay? And we're going to continue working with this, so we get 1 minus 2t, and then 1 plus 3t, and 4 plus 5t, okay? So this is our r1 of t, okay? So that's what we have now, and these are our parametric equations. So this is our x, that's our y, and this is our z. So I'll continue on the next slide. So then we have r2 of t, and this, when it's written, when you do some algebra, it's going to turn out to be negative 5 plus 2t, and then a 0 plus 2t, so just a 2t, and then an 11 minus a t. Okay, so now we want to find, is there a t1 such that t1 and t2 such that r1 of t1 equals r2 of t2. Okay, so what we actually have, let's say, so from the previous slide, I'll just write them down here. We had 1 minus 2t, and I'll write like a little subscript of 1, just to reaffirm that we're working with r1 on the left side. And then our next component was 1 plus 3t sub 1, and then 4 plus 5t sub 1. Okay, so that was for r1 of t. And then on the right side, I'm just going to rewrite this, but just write t sub 2 instead, just to show that we're working with r sub 2. So negative 5 plus 2t2, and then 2t sub 2, and 11 minus t sub 2. Okay, so what we want are these to be equal, so that just means the x's have to match up. Sorry, there's a 1 there. The y's have to match up, and the z's have to match up. And we're going to see if that actually works out. So we're going to do the x's first. So we have this. It must be equal to this, okay? And then, so this is for the x's. For the y's, we have the following equation. 1 plus 3t sub 1 equals 2t sub 2. And lastly, for the z's, we have 4 plus 5t sub 1 equals 11 minus t sub 2. Okay, so now that we have these three equations, this is basically a system of equations problem, okay? And again, you might have seen this in Algebra 2, system of equations, okay? So we can just do like substitution or something like that, right? So I'll work with the first equation, or we'll start with the second equation actually, okay? So we're going to start with this, and we're going to say that we actually see this 2t sub 2 in the first equation. So we can just replace this thing with whatever we see on the left side here, because these are equal, right? So we're just going to sub in, so we have 1 minus 2t sub 1 is equal to negative 5 plus, and we're going to plug in this thing for 2 times t sub 2. So that'll be 1 plus 3t sub 1. Okay, we just substituted that in. And now see how we're down to just t sub 1s as our unknown in this equation, so we can solve for that. And we actually just get, let's see, what do we have? So we have a negative 4 here, where the negative 5 plus 1 is negative 4, and if we add that to the left side, we get that equals, let's see, a 5. And then we have, if we add the 2t sub 1, add 2t sub 1, we get that equals 5t sub 1. So t sub 1 is equal to 1. All right? So now, let's go back and solve for t sub 2. So we'll pick, let's see, what should we pick? The first equation, I guess. 2t sub 1 is equal to negative 5 plus 2t sub 2, and we're solving for this. And we already know that this is equal to 1, or should be equal to 1. So 1 minus 2 times 1 equals negative 5 plus 2t sub 2. So that's going to equal negative 1 over here equals negative 5 plus 2t sub 2. We add 5, just doing some algebra. So that'll be a 4 equals 2t sub 2. So t sub 2 is equal to just a 2. All right? So now that we found that, and we know that t1 should be equal to 1, let's go back and check that the points actually do match up. So we had 1 minus 2 t sub 1. Remember, we had all t sub 1s on the left side, all t sub 2s on the right side. So then the next component was 1 plus 3 t sub 1, which is now a 1. And then we had for our last component 4 plus 5 t sub 1, which is now also a 1. Okay, so that does it for our left side. And now for the right side, how we set that up is negative 5 plus 2 t sub 2 should be a 2 now. And then 2 times t sub 2 is now a 2. Sorry for all the 2's. And then our last component was 11 minus t sub 2, so that's also a 2. So let's see if these actually do match up. That's the question. So we have 1 minus 2, so that's a minus 1. Here we have 1 plus 3, that's a 4. And then we have 4 plus 5, so that's 9. Does this equal negative 5 plus 4, negative 1? 2 times 2 is a 4, and 11 minus 2 is 9. So yes, they do match up. And so that means that they're at the same point, and this point looks something like, so if this is x, y, and z, x, this would be going in the negative x direction, it would be going 4 here, and 9 here. So yes, they do intersect at some point. Sorry, that was a really bad line. So here's this point here. Let's say the lines look like that. They do intersect here. Okay? So we did find, again, I'll write them down here, t sub 1 equals that, and t sub 2 equals this. So these lines do intersect at some point.